circles and parts of the circles here for this set of slides. By definition, a circle is the set of all points that are equidistant from a given point, called the set. The set of all points that are the same distance back to a given point, called the center. So in the diagram, I've got a circle whose center is this point, and every point on this circle is the same distance back to the center. Any point on the circle, back to the center, that distance is always the same. A couple of different distances within a circle to know more about. I'm sure you've seen these words before. Radius and diameter. How do we name that distance between the center and any point on the circle? What is that named by? From the center to any point on the circle. That is known as what? From the center to any point on the circle. That circumference is from the center to any point on the circle. That is called the radius. And no matter where on the circle you're talking about, isn't the radius always the same? This distance from the center, this point on the circle is the same as the center. This point on the circle, as from the center to this point on the circle. Any radius of the same circle is always the same one. Radius is the distance from any point on the circle back to the center. The diameter of a circle is a line segment from one end to the other that also passes through the center. Line segment from one end of the circle to the other, passing through the center. Here's an example of the diameter. How does the diameter relate to the radius? How many radiuses are there in a given diameter? How many radiuses make up a diameter? Two. There are two radiuses in every diameter, right? So the diameter is twice as long as the radius, or the radius is half the diameter? Yeah, because isn't the diameter twice as long as the radius? There's two radiuses in every diameter. And too groundbreaking, I'm sure you've seen that before. On your formula sheets are these two formulas for circles when it comes to area and circumference. The area of a circle is given by pi times the radius squared. Pi r squared is the area of a circle. The circumference of a circle refers to what? What does the circumference tell you about a circle? Second time? Yeah. Isn't the circumference just the perimeter of the circle? If you were to walk around the circle, the circumference would be how long you would have walked. Length you would have walked. The circumference, or distance around the circle, can be found a couple of different ways, using either pi times the diameter d, pi times d. Or since the diameter is just twice as long as the radius, I could use 2 pi times radius r. These formulas are also on your formula sheet, pi r squared for the area, and the circumference given by pi times the diameter, or 2 pi times the radius. Space inside and distance around, area and circumference. All right, let's talk more about lines and segments. Tangent lines, secant lines, and chords. Different parts of a circle. Tangent lines, secant lines, and chords. A tangent line is a line that intersects a circle exactly once. There are 2 lines in that figure. Which one is the tangent line? The green or red? Which one is the tangent line? The red line is the tangent line. I agree. Doesn't it kind of just skim off the circle? Just briefly touches it right here. Kind of kisses off the side. This is a tangent line because it intersects the circle exactly once. Where the tangent line intersects the circle is called the point of tangency. Where the circle and tangent line intersect is the point of tangency. Also noteworthy about tangent lines. Tangent lines are perpendicular to a radius of the circle. So if I look at this radius in pink and the tangent line in red, it forms a right angle, a 90-degree corner. Every tangent line is perpendicular to a radius of the circle. If the tangent line goes through once, intersects the circle once, how many times does a secant line pass through a circle? Twice. That's why it's a secant line. It goes through twice. That's how it's different than a tangent line. In green, I have a secant line. It passes through twice and forms a secant line. Two types of lines, tangent lines and secant lines. A chord is a line segment. It does not extend in two different directions. It's got a starting point and an ending point. And what makes a chord is it's a line segment whose endpoints are on the circle. Starting point and ending point of a chord are on the circle. So in blue is an example of a chord. Left endpoint and the right endpoint are 2 points on the circle. This is a chord, C-H-O-R-D, chord. A line segment whose 2 endpoints are both on the circle. That's what's known as a chord. Couple extra tidbits about chords. A diameter is a chord that passes through the center of a circle. Every diameter is also a chord, but not all chords are diameters. Is a diameter a line segment whose endpoints are on the circle? So let's take a look. Here's the diameter. Are the left and right endpoints of the diameter on the circle?
Yes.
Yeah. So is a diameter also a chord?
Yes.
Yeah, it's just a chord that happens to go through the center. It's a specific type of chord. Every diameter is also a chord, but not all chords are diameters. For example, that blue chord is not a diameter. Another piece of info, every secant line contains a chord. Look at this green secant line. Why is it called a secant line again? It passes through a circle twice. Well, what if I just cut off the secant line where it intersects the circle? I'll cut off the secant line here. Cut off the secant line here. Isn't this green line segment now a chord? Yeah. A secant line is made up of a chord. If I cut the secant line into a line segment where the endpoints of the segment are on the circle, now it's a chord instead of a secant line. Right. Let's make sure we got this here. Tangent line intersects the circle. Once secant line intersects the circle. And what's important about a chord? The endpoints are on the circle, on the circle, on the circle. Tangent lines, secant lines, and chords. Today and tomorrow, we're going to get into arc measure. So let's talk about how we can classify different arcs of a circle. In general, an arc of a circle is a portion of the circle's circumference. It's not all the way around, it's part of the way around. BC is a piece of the curve starting at B, ending at C. Arc BC is a portion of the circumference. One endpoint is B, the other is C. When I label an arc, I use the 2 endpoints, a little curve on top. What I know, it's the part of the circle whose endpoints are B and C. From B to C, that piece of the curve itself. I can classify an arc by either minor arc, major arc, or semicircle, based off how much of the circle that arc represents. A minor arc is an arc whose measure is less than 180 degrees. This BC minor arc is less than 180 degrees. How many degrees is a full circle? One whole rotation in degrees is how much? 360, that's a full circle, right? What would half of a circle then be? 180. So wouldn't a minor arc just be less than half a circle? By definition? You bet. Isn't this piece of the circle from B to C less than half of the whole thing? Right. Now a major arc is just the opposite. A minor arc is less than a half a circle. A major arc is more than a half a circle. A major arc is an arc whose measure is more than 180. So the major arc in that diagram is arc BDC in red is the major arc BDC. Do these two arcs have the same two endpoints? They do. So how do I know the difference? What does the D tell me about the arc that I'm trying to do? So I'm not going directly from B to C, I'm going the long way around, right? From B to D back to C, right? If you're going to name a major arc, don't you have to tell the reader to go the long portion? So you need an extra letter, right? From B back to D around to C. That's a major arc because it's going to take up more than 180 degrees, more than a half. A minor is less than a half a circle, a major is more than a half a circle. Exactly a half a circle is called a semicircle. An arc that's exactly 180 degrees is a semicircle. Semicircles are cut off by diameters. So on this diagram, EFG is a diameter. And it cuts off two semicircles. The top in green, GHE, and the bottom semicircle in black, EJG. Both of those are exactly 180 degrees. We've got arcs. We've also got sectors and segments, pieces of the total area. I could cut off a portion of the area as a sector or as a segment. A sector, I think, looks kind of like a pizza slice. Doesn't that green sector look kind of like a slice of pizza? Yeah. By definition, a sector is a portion of the circle that's enclosed or cut off by two different radii and an arc. This green sector is closed in by the radius on top, the radius on bottom, and the arc here on the left side. The arc is kind of like the crust of the pizza. A segment of a circle is any portion of the circle that's cut off by a chord. A segment is cut off by a chord. So this blue segment is formed by cutting the circle with this line right here. That is a chord. To me, the segment looks kind of like a thumbnail almost. I don't know. You ever need these definitions? I've got this slide linked on Google Classroom. Last set of information here. Angle measures. We're going to talk about later in this unit central angles and inscribed angles. So what's the difference? A central angle is an angle whose vertex is at the center of the circle. Doesn't central mean center in the middle? That's what central means. So it makes sense that the central angle is an angle whose vertex is center of the circle. The vertex is the corner point for the angle. The vertex is the corner point. So which one of these two angles, red or blue, is the central angle? Which one is the central angle? Is it the one in red or blue? Blue. So what's the vertex of the blue angle? Is it A, C, or O? Which one's the corner point, the vertex? O. When you label an angle, you use this notation. That is the geometric notation for angle. And I name an angle by putting the vertex in the middle. AOC, the blue angle, is the central angle because O is where? What's important about O when it comes to that circle? It's what? The center. What's the inscribed angle? An inscribed angle, the center is now, it's on the circle, right? In an inscribed angle, the vertex is on the circle. Which one is the inscribed angle, blue or red? So what's the vertex for the red angle? B. The corner point of the angle, the vertex, is on the circle. When I name the inscribed angle, instead of AOC, now it's ABC. Later in this unit, we're going to talk about how central angles and inscribed angles are related to each other. Obviously, the inscribed angle is smaller. We'll see it's smaller by a certain factor. Questions so far? Here's your task. On the next slide, here's the first question on your test. Pretty much exactly this. There are different parts of the circle you're asked to label. Each of those colored arrows is pointing to a different portion, different part of the circle. Fill in the missing labels with the word bank below. Does that make sense? Fill in the missing labels with the word bank below. I think it's probably easiest to just do this by naming the color. So for example, green arrow. What is the green arrow pointing to? What word goes in this box? Tangent. Green arrow is tangent. That's fine. Or you can just draw the picture if you really want to. It's all the same. Take about 4 minutes. I'd like you to fill in those missing boxes. The red is, okay, that's a good question. This is a little bit deceiving, I think. You see how the pink arrow is pointing to this bolded portion here? The red arrow is the entire circle, this entire distance. Does that make sense? What color is that? We can talk about this. What do you call that color?
Teal.
Teal, turquoise, maybe? I don't know.
Teal.
Sea green, somebody said earlier? That is blue, though, right? No. The purple is pointing to the area here. That region. The orange points to this line segment. What is the name of this type of line segment? go around the horn here. I'm going to start at the very top, the noon hour here. Where do you think this yellow arrow points to? Radius, I agree. Anthony, how about this turquoise, is what we said earlier? What do you call this one? Diameter, you bet. Max, we said green was what? Tangent. What about this orange one here? What did you say, Zoe? Chord, it is a chord, very good. A chord is a line segment whose endpoints are on the circle. The chord is cutting off this purple region. What do you say here, Tom? Sector. Sector, I agree. Destiny, do you have the red one? No? Somebody help her out. We're talking about the entire distance around the circle. The circumference, you bet. The circumference is the red one. The circumference is the red one. Sylvie, did you have this blue one right here? Segment was actually the purple down below. The blue one is kind of like a pizza slice because it's being cut off by the radius going up, the radius going left. It's a sector. It's a sector.
Oh, you said the purple one was sector.
Segment. I said segment for this one earlier. Sorry, I misheard that. The blue one is a sector. Do we have that right now? And then, Kira, you finish this pink one up on top. It's not the whole way around, it's just this bolded portion that's cut off from the rest. Starts with an A. No, area is not up here. A portion of the total distance around the circle, a portion of the total circumference is known as an arc. This is an arc of the circle. It's like a little piece of the pizza crust. A portion of the total circumference. So we had radius, diameter, tangent, chord, segment, circumference, sector, and arc. Is that right? Going from top clockwise around the circle. Okay, then let's do this. On the board behind me, today and tomorrow, I want to get into arc measure and central angles. So let's run through a couple of these. I got a set of examples to get us started on circles. The first two questions are asking us to do just the opposite. On number one, name the arc made by the central angle. Angle AED opens up to what arc measure? On number two, name the central angle that matches this arc. Just the opposite of the first one. So the first one, name the arc formed by the central angle AED. It's a central angle because where is E? What is important about point E? It's the vertex, and if it's a central angle, the vertex is at the center. So let's start at E and open up that central angle. I'm going to start at point E and follow along the sides of the angle. Angle AED opens up to what arc measure? What arc is this? At the classification, name the arc, use the letters, use the endpoints of the arc. It's arc A. Central angle AED opens up to, if I follow along the sides of the angle, this arc measure. It's a minor arc, AED. AD. We're trying to look. We got it. How about angle BEC? What arc does that central angle open up to? BC. We're at the center. Go along the sides of angle BEC, and doesn't it kind of make that arc BC? Example 2, just the opposite. Rather than giving you the angle to match the arc, I want to have the arc to match the angle. Name the central angle forming the arc WY. Here's arc WY. I outline that. Again, yeah, you're just kind of collapsing it back in. Angle W, Z. All right, arcs and central angles, very related to each other. They have the same measure. On this last example, we're going to get into arc measure. How many degrees is each of these arcs? What is the measure of arc OP? What is the measure of arc ON? What is the measure of arc OL? We've got a couple of legal angle measures. 120 degrees in blue and 55 degrees here, just to the right. Some other things that might be helpful as I look at this. A full circle is how many degrees? 360 is a full circle. How about a half a circle? A semicircle? 180. All right. Got that. OP, the measure of arc OP, that is this portion of the circle. Right here. Any thoughts on how I could find that measure based off of what I've been given so far? Yeah, so let's assume that everything looks like a diameter is also that.
And L is central angle.
Okay, so how can I find OP? What do these two arcs have to add up to? 180 because it's a semicircle, right? So if the two arcs make 180 and one of them is 120, what's the other one have to be? 60 because it is just the difference. If the whole thing makes 180 and one of the two parts is 120, the other part is just 180 minus 120. So we'll put 60 here. I guess I'll put 60 up on top too, since those have to be the same thing. One down, let's move on to the next one. ON.
We're defining the minor.
Yeah, assume if there's only two letters, Tommy, that it's the minor arc. The last one, when it says OLN, you know that's a major arc, right? ON, what would ON be? How could I get ON? Well, let's maybe play that same semicircle game again.
Minus F alpha 180.
Minus 180, and then, what am I taking away from 180?
60 and 50.
Yeah, there's three pieces. I know two of them. Find the third by just subtracting 180. Take away 60 and 55. What do we get? Nothing to it. Now Tommy's kind of leading me to my next point here. What's important about OLN? How do I know to go the long way around? The L in the middle, right? Go from O to N, but you have to pass through L to do it. So it's going to be from O through L, ending at N. How can I figure out that measure? Subtract what?
65.
So isn't OLN everything but ON as a minor arc? What does the entire circle have to add up to? I want all the 360 but the 65, right? Someone else said add them all up, but add up everything but 65, right? Add up 60, 120, 60, and 55. Would you get the same thing there too? I don't know, I think it's pretty easy to take 360 minus the one I don't want to include, so just 360 minus 65. We get there. 295. Obviously a major arc because it's more than. You bet. I like it. All right. So here's a couple things we can do.